So tonight we are really fortunate to have two HVO scientists and affiliates. Lopaka Lee, geophysicist, geochemist, IT specialist, many things. And Dr. Cheryl Gansecki of UH-Hilo, Geology Department. Hometown favorites. Lopaka and Cheryl together formed the tip of the spear, so to speak, in 2018, looking at the geochemistry, the petrology of the lavas that were erupted in Leilani Estates throughout the entire eruption. So tonight, the two of them in tandem will present a talk entitled, if I can find the title, What Can Lava Tell Us? Deciphering Kīlauea's 2018 Eruption Through Chemistry.
Well, we have a nice crowd. I'm kind of surprised because Jen and I had gone back and forth about the title, and we were convinced that if we included the word chemistry, we cut it in half, with the amount of people that show up. Everybody said, I don't like chemistry, I failed chemistry. But I thought what we do, Cheryl and I, is we break up the talk, and I would talk more just about the background, about petrology, geochemistry, and also the project that we have between UH and HVO. And then I'd let her talk about all the hard stuff. She could actually talk about the data. So yeah, I'll just stand up here and I'll talk a little bit about geochemistry and petrology. Geochemistry is, of course, the study of the chemistry of Earth materials. Not only includes rocks, soils, water, sediment. And petrology is a subdiscipline of geochemistry, specifically that studies how rocks form. Now, our work during the eruption led to a lot of really great science. And there's still publications coming out about it. But just a month ago, we were published, there were 3 papers that were published in a bundle within Science. And Science is a very prestigious magazine. And these articles, or these publications in here, highlighted the great work that HVO does. It highlighted a lot of the great science that we do in collaboration with universities. And it was just a really neat thing to see. Cheryl was the lead author on the paper in that bundle. But the 3 papers that came out in there are 3 different topics. One was on magma reservoir failure, which detailed how the caldera collapsed and its effects downrift. Another one, which was by Matt Patrick. The first one was Kyle Anderson, the first author, and the second Matt Patrick at HBO was cycles of lava diffusion, which had to do with pulsing of lava down in the East Rift that happened as a result of things collapsing at the summit, and also degassing, which was causing cycles of the lava coming out and fusing. And then, of course, Cheryl's paper, which she was lead author of, which was on magma mixing in near real time. Now, that part of it, that near real time part of it, is really what the journal found really novel or unique. And so I'll talk a little bit about that, as to why doing it in near real time, talking about the magma, characterizing the petrology and geochemistry in real time was so unique and different for this eruption. In order to understand that, you have to understand, well, what is volcano monitoring? And what is volcano response when an eruption happens? And at HVO, we're divided into subdisciplines, and we're all focused on monitoring the volcano and responding to eruptions. But our primary tools are really largely geophysical tools. We measure ground deformation, or the way the surface deforms as a result of magmatic activity, or ground motion. Our primary instruments are GPS, also tilt meters. We measure seismic activity using seismometers, earthquakes with seismometers. And we also do gas geochemistry as well, too. And that measures gas as it's emitting from the volcano and can tell us a little bit about where the magma is relative to the surface. And all these things have been a part of our normal monitoring routine that we use at HVO. And generally, the geophysics-based methods like ground information seismic activity or seismic data from seismometers come in as real-time streams. So once we set up the instrument, these data streams are coming in, and we're able to sit at the observatory and watch them in almost near real time. And gas emissions, too, generate some fairly consistent, regular data, which we also import into the system, and we can watch that. Geological observation is also a key part of that. And I like this diagram here. If you're a geologist, you get to ride around in a helicopter all the time. And that's true, the geologists get all the glamorous jobs. They ride around in a helicopter. But in this diagram, at least, petrology and the geochemistry of the rocks is not explicitly stated in there, of course, because as you can imagine, it's not necessarily the same. And it's a little more difficult to fit it in within that framework. The reason being is that studying lava chemistry is typically a much, much slower process. And it's usually a retrospective tool. So usually people use it to study eruptions that have already happened, or even as they've happened, you won't look at the data or publish the data until much, much after. And, you know, it has to do with the fact that it's a difficult thing to do. It's a difficult thing to do well, it's a difficult thing to do quickly. This image here shows cutting rocks. You've got to cut rocks in order to look at them under a microscope and characterize the minerals that are in there. How many people have you made a thin section? Right? Oh, quite a few, yeah. It is hard. It is hard. You have to cut wafer thin slices of rock, then you polish them down, and you polish them down, you keep polishing down until a paper thin. And they have to be a particular thickness, not just any thickness. Okay? And then once you do that, you're not even done. You just started, you know? Then you put it on a microscope and you can see the minerals in there and start describing them. So it's very laborious. Obtaining the chemistry of the rocks is also something that's really, really laborious. Usually, most of the methods, you can't just pop a rock in there. There's some exceptions I'll describe. But you normally can't just pop rocks in there and get the data back. You've got to prepare them somehow. That's what this technician's doing here. He's preparing the sample for some kind of analysis. That involves time. And then the biggest thing is that the instruments that you use, they're not just expensive. They're like exorbitantly expensive. We're talking about multi-million-dollar instruments typically. So they are housed in labs very far away, centralized, so that everybody can use them. And that's the other problem too, is that you're not the only one. Everybody else is standing in line to use these instruments, you know. And so when you come to, and you say, we've got an eruption, we need our samples now. I say, yeah, well, get back in line. So that makes it hard as well to try and provide geochemistry and petrologic information in a rapid manner, particularly when an eruption is occurring and events are unfolding. And that's why it was so novel, what we did. But even though I was focusing on the fact that it's not a rapid technique, but it's a solid science, right? It's told us a lot. Petrology and geochemistry has told us an immense amount of information about our world around us, and some of it is just absolutely key to our understanding about the way certain Earth surface processes, Earth processes work in general. And of course, the Hawaiian Islands, much of our understanding in the Hawaiian Islands comes from the chemistry of rocks. Everything from the nature of the hotspot, its composition, and also the ages of the islands. We determine through chemical analysis of rocks. So, how do we do that? And so I'm going to attempt to describe, at a very general level, how we do that. And normally, we would say you can't really do that in a single talk. I'm going to do it in a single slide. I'm going to attempt to at least. Basically, we all know that magma is liquid rock. And as that liquid rock cools, important major things happen. And you can tell basically a lot about the history of a rock after it's cooled by looking at its chemistry after it's gone through that cooling process. So up here, we have a magma of composition A, right? You can imagine this thing being underground. And as it cools, minerals start to precipitate. There's certain minerals that precipitate. First, one of the primary ones that we're probably all familiar with is olivine. And when you go out on the beach, you'll see little green olivine specks there. That's one of the first minerals to precipitate out first. When that forms, it actually captures the chemistry of the liquid that it's around, right? Because it's forming in that liquid, that magma. And so if we look at the chemistry of that olivine, and we look at specific elements in there, like for example magnesium, so the primary elements in olivine, and iron, if we take a look at the ratio of those two, we can tell something specifically about the temperature under which that olivine formed. So this process goes on, and additional minerals will form, right, as the magma cools. And if it's left to cool all by itself underground, eventually it would end up with this interlocking mesh of crystals with very little liquid left in there, right? And a lot of the composition of that magma, the different parts of its chemistry, the different elements will have gone into different parts, different minerals, because each mineral has its own composition and it wants something from the liquid. And so if you measure, again, composition of the mineral, composition of the liquid, you can infer something about the way it formed. And within the context of this talk, some of the most important pieces of information that we use or we derive from this is temperature, right, of the magma, when it was cooled or quenched, also sources using chemical fingerprint, and then a little bit about the history, what happened to it before it got to the state it's in. So it turns out that we've been actually doing this rather routinely on a regular basis for a long time at HVO. Before Pu'u'o, it was a normal part of just responding to an eruption, right? Is to describe it in all forms, including geochemistry and petrology. But Pu'u'o really changed things, and that was a continuous eruption, 35 years of continuous eruption. And during that time, it was for large stretches, for long stretches, it was like a walk-up volcano, right? It was walk-up sampling. And Ken Hahn, who's sitting back there, likes to joke about the Kapaiana'a days, where there was a lot of liquid. He was able to say, yeah, you could just walk up to the thing and just throw a hammer in with a chain, and there you go, and then eat your sandwich. You have a sample, you can imagine that. And
short work days, I like it.
yeah, right. Well, it's a lot harder than it looks, actually, to show it. But we still have easy access to an active volcano. And so really that set the stage for continuous monitoring, if you will, of lava chemistry. And that was done for all of the eruption, all 35 years it was done. And this involved, multiple generations of geologists, which included Ken, and Cheryl, and Tina. You were part of that effort. Actually, yeah, I looked in the database, and your name is under a lot of samples in there. Yeah. So, many others, two-time students and collaborators have come to help in this. And it generated an enormous database, which we're still interpreting today. So, that happened, but we were still, as of late, within the last maybe 10, 15 years, there was a desire to kind of turn it around even quicker. And particularly within the last 6 years, we really started getting focused about, well, how can we do this faster? What can we make fast? What can we, how quick can we get it? And we started that discussion with UH-Hilo because this is one of my favorite sayings about instrumentation is if you've got a hammer, everything becomes a nail. Meaning that you use that hammer, you just bash everything in submission. But no, it's actually, it's kind of a double-edged thing. It's that if you have these resources, you really should be using them. You should be trying to figure out how best to use those instruments, right? And we had this collaboration. We had a long history of collaboration with UH-Hilo, but when we started thinking about this, there was a couple of things that happened. One is that there was an instrumentation that was available. There were people that we've been working with, but then there was new instrumentation that was available that would make it easier for us to analyze things. And one of the key things was this thing called an EDXRF. It's an energy dispersive X-ray fluorescence instrument. And this is Professors Peter Mills and Steve Lundblad. Steve's back there. Peter's here. Yeah. And Ken, you were a part of the EDXRF acquisition as well too. And what they were doing was getting back to this hammer analogy, is that they were using these things to actually analyze hammers. They're actually stone hammers, stone adzes. And the reason why they used it is because it was quick and it was non-destructive. So they could take adzes, they could take stone artifacts, quickly put them in this thing, analyze the chemistry, and from that they were able to discern where these different materials were coming from, where these different rocks were coming from. And that's, I think, was sort of the plant of the seed. I can't remember, but it was like, hey, if they can do this, why can't we do this with lava sand? And so that really set the stage for that. So we started formally in 2012. The formal beginning of the HVO UH Petrology project. And basically, the routine involved HVO being responsible for obtaining samples, and then we bring the samples down to UH-Hilo, where we go through this routine of analysis that we developed over time, over 6 years of working on this actually. We developed this and refined it to get us back chemical information. And so we did it in really two, I forgot, yeah, okay, this is a nice break actually. Before I describe how we did it, I'll talk about lava sampling. Remember Ken Hahn said that it was super easy. So this is Professor Bruce Houghton from UH Manoa, and we put him up to this. We said, Bruce, go get us a sample there. Here's a shovel. All you got to do is just take a quick shovel and put it in the bucket. It's no problem. And actually, he does a great job. Quickly, put it in the bucket. And right now, his face is burning. His face is almost burning off, and he's playing it off.
I have a fan and a shovel.
Just drop it in it. I love that about that. Yeah. So we quench it really quick. We take a sample and then we put it in water really quick to freeze it immediately so it doesn't change anymore. Oh. Okay. So our routine involves two basic paths we call or routines that I'll call fast twitch and slow twitch routines. The fast twitch routine involves using this EDXRF. So we get the sample, get it to UHs, and as quickly as possible, regularly as possible, we power the sample. And then we put it on the EDXRF. And then from that, we get a suite of elements that are able to tell us an awful lot about the rocks. Now, EDXRF, you can't get everything you need out of that instrument, but you can get enough, and as Cheryl will show you. During 2018, we surprised ourselves with the kind of information we could get out of it. The other part of it was a microanalysis routine, which is more of the slow twitch routine. This is more of a traditional type petrology routine. So we were picking individual minerals out of samples, right, to characterize it, and glass, and we mounted up in these grain mounts, and we had some innovations on that too. We came up with 3D printing rounds and things to kind of speed it up and pack as many as we can, and we put those rounds into epoxy, polish them all, and then we put them on the SEM, scanning electron microscope, to look at them in detail, and that's also available at UH-Hilo as well. And then we would select what points we want to probe and get the chemistry, and then we send that off to the really expensive microprobe in Denver, and then the data would come back. So that was sort of a slow twitch. Obviously, you can't do this without help, and we've had a lot of help. And a lot of different students have helped over time. And not just these students, people have been sort of sucked into the vortex, you know. If you're standing around, you're going to help, particularly during the 2018 eruption.
Why is Derek a
Derek. So I didn't have any I know, Derek. Yeah. So yeah, Derek was from Louisiana. Yeah. He's a jambalaya. And I didn't have a photo of him. I didn't, so I just...
I got a picture of Mickey better than that one.
Yeah, I'm sorry. Yeah, so Mickey's here as well too, but I spared you the indignity of a real photo. Lil Smither is now with us at the observatory, and then Brenna is here on island. I guess she's doing
right there?
Oh, whoa! Hi, Brenna.
Hi, how you doing?
Hey, it's good to see you.
You too.
Yeah. Wow. Cool. Okay, and then Valerie is now at Fairbanks, Alaska, studying volcanology, and then Ryan, I think, is off doing mathematics or something. He was always really good at math. Yeah. So, thank you for being a part of the project. Yeah. All right. So now, after that background, I'm going to hand it off to Cheryl.
So now I'm going to segue into 2018 and what happened and what we ended up doing, and what could the lava tell us? It turned out in the end during this eruption. Samples and methods, you heard mostly about that. In this particular eruption, the HVO and all the field crews collected 113 lava flow and spatter samples during the eruption. We analyzed them during the eruption as soon as we could. There's Bruce again, collecting spatter samples, and Katie collecting lava, and there's Mickey in the corner. Better picture of Mickey there on the EDXRF. So it turns out there's certain key elements I'm going to be talking about, and I apologize in advance for all the graphs, but they'll all link together and make sense, hopefully, for you. But there's kind of 5 elements up here that I'm going to talk about. And there's basically 2 categories of them. So we've got potassium, titanium, and zirconium there as one group. Those are what we call incompatible. And we've got another group here, magnesium and calcium, we call compatible. So these are elements we could get with EDXRF. We could get pretty good numbers on. Magnesium's a little messy, but it's so important we could get it anyway. We could still get good enough numbers with it. And those 2 categories tell us something a little bit different. So let me try to explain the idea of incompatible versus compatible. So Lopaka talked to you about how magmas evolve over time, and the crystals grow, and it changes the chemistry. I like to think of it as a magma is basically like a bag of trail mix, right? It's basically a big mix of elements mixed together. And if you think your average bag of trail mix, right, it's mostly peanuts and raisins, and it's got some good stuff. It's got some M&Ms and some cashews. Some trail mixes might have something weird. Maybe you got broccoli chips or something that nobody's going to want to eat. Okay, so our magma's got a little bit of everything. So now we picture our magma sitting there beginning to crystallize. Things are being removed. So we hand our bag of trail mix over to our friend Olivine. Olivine loves M&Ms. Starts eating out all your M&Ms. You might get some of the peanuts and other stuff too, but eats out a lot of your M&Ms. Passes it on to some of the other crystal friends, right? They really like M&Ms too, maybe some cashews. And they're eating a little bit of other stuff. But by the time you get the bag back, there's a lot less material, and it's really concentrated in peanuts and raisins. All your M&Ms are gone, and nobody touched the broccoli chips. Okay? So in our analogy here then, zirconium is our broccoli chips. Nobody wants it, right? It just gets left behind. Magnesium and calcium, that's our M&Ms and our cashews. Crystals love them, they want to eat them up, they go away pretty fast. And so those two guys are kind of two different fingerprints, and they're going to tell us different things about our magma as we go. Okay? So, we'll start with the beginning of the eruption, May 3rd, 2018, Fissure 1 rips open through Leilani Estates. The magma, the lava that comes out, they're not very big eruptions, certainly destructive, but they're not very big, and the lava doesn't travel that far. So here's, I'm going to show you a series of maps as this eruption evolves. So here's Leilani Estates. In yellow here is the lava that comes out during the first week of the eruption that we're calling early phase 1. This is the initial 15 fissures. So 15 different cracks open up all in a line, kind of back and forth. And the lava that comes out is kind of cool, sticky, a little bit nice explosive fountains. One bigger flow comes off of Fissure 8 and then stops. So what does the chemistry look like? Okay, don't panic. They're just plots. The top one here, we'll start with this one, is our zirconium, right, our broccoli chips, versus our M&Ms, the magnesium. And this little gray zone right here, this is the last 10 years that have erupted out of Pu'o'o, to give you a sense of where things are changing. So this is where Pu'o'o was sitting, kind of higher magnesium, pretty low zirconium. So as soon as those first lavas erupted, we got the samples back, we stuck them in the machine, I got the first numbers back, and I was like, yes, it's exactly what we thought it was going to do. High zirconium, low magnesium. This is not your Pu'uo'o magma that's coming out. This is something different. And it's what we actually expected. This has happened before down in this area. We're kind of low on the rift zone. We know old magmas might be down there. They cooled off. They lost their M&Ms, and they end up as this different composition. So we saw that right away, and that was exciting. This figure down here is going to be now, this is the temperature that we actually use calcium to estimate, so we can again use that element to give us an estimate of the temperature. And then this is just going to be progressive days as it begins. So this is 0 is the beginning of the eruption, and just going to go on up from there. This gray band is the average Pu'uo'o temperatures from the last few years. So they're up at about 1150 Celsius. This initial 15 fissures erupted at about 1110 Celsius. Okay, so big temperature drop. Clearly not the same thing. When magma is cold, when lava is cooler like this, it's stiffer, right? It's got a higher viscosity. It's not going to flow as easily. So this actually, it tends to have maybe some repercussions for hazards in terms of cold lavas are not going to flow as easily, so they won't move as fast. But they can potentially, really stiff magmas can get explosive because the gases can't escape, so they'll build up pressure. So there's always that kind of, as you get too cool, that can happen. At this point, though, the lavas were just kind of slow, kind of sticky, but we were already pretty sure that what we were looking at was stored magma from previous eruptions. Now we don't know which previous eruptions, but we know it was stored. Now there was a couple days break in the eruption, and then it restarted again on May 12th, down rift, so to the northeast here, up in this area. Now this is the green. The black lines are the fissure segments. And so again, pretty small little lava flows, kind of probably even hard to see right now from here. Still pretty sticky lava. So this goes through about the 17th, fissures 16, 18, 19, and 20. We'll get to 17 in a sec. So here's in green is our new lava flows. And what we see immediately is there's a change between those initial fissures and the second group of fissures, right? Things are definitely, they're hotter. It's about 20 degrees hotter on average. Right away we could see that. And when we look at the fingerprints, we see, okay, it's starting to shift more towards Pu'uo'o-like compositions. So at this point, we knew we're looking at lava that's hotter. It's possible that it's likely that what's happening is this old sticky stuff is getting mixed up with some hotter stuff coming down the pipeline, and it's starting to shift. And so we actually, when we saw that, put out a notice on the communications platform that HVO was using for people in the field, just to note that we've seen this increase in temperature and, you know, possibility for things to heat up and get moving a little bit faster. At this point, we're all pretty sure that the thing hadn't really gone as big as it was going to go. But we can see that, and that was a neat thing to see. Now, kind of starting at the same time, fissure 17 broke open, which is this thing up here. So it's the one fissure that was offset from the rest of the fissure trend out here. I don't know what they call it, on echelon step, where it steps sideways. And it erupted something unique, something that we've never seen erupt on Kīlauea or anywhere on this island before. Very unusual behavior, it's more explosive. It sort of overlapped the phases of the rest of the eruption, this phase kind of 1 and 2, but it was this unusual behavior that made us very interested in the chemistry. And sure enough, when we saw the chemistry, well, was that you, Mickey, that did that one? You brought me the data, and I was like, you did it wrong. Go back and do it again. That can't be right. Because that can't be right. And because we've never had anything that high on this volcano before, up at 500-600 parts per million of zirconium, right? That's a lot of broccoli chips. And so very unusual kind of thing here. And when we look at the temperatures, they're very, very low, around 1060 to 1080 down in here. Part of it was erupting at a slightly, you can see there's quite a range of compositions. So it's very interesting. We're still trying to figure this out about this particular eruption section of the eruption, the fissure 17, because there's a wide range of compositions. And so what that means, there's a lot of questions about that still. But definitely we saw some very, very, we call it evolved, the stuff that's really had everything taken out but the broccoli chips. So what does that mean? It means our lava is very cold, very viscous, and suddenly it makes a little more sense why it's so explosive. I'll show you a little bit of video here, just from this vent, just because it's so cool. But it's clearly had a lot of gas in it. It may have had some groundwater involved as well, but the fact that it only happened where you had this super, super sticky, viscous, cool lava, I think implies that they're connected. So here's the main vent, which is erupting the little hotter stuff out of the main fissure 17 vent. And this section of the fissure 17 is where the really explosive, really, really evolved stuff was coming out. So you can see a burst come out right in here. These big explosive pulses that really were quite a thing in the field. So those things were flinging rocks pretty far. It's very explosive and very unusual. So it's a type of rock we call an andesite. So most of our lava is a basalt. This one was erupting andesite, something that I've got a few petrology students here. You'll learn to know intimately. But this is the only one we've ever seen on Kīlauea or Mauna Loa or any volcano on this island. So it's really quite unique and a pretty amazing thing. And what it means, there's a lot there. Okay, but then we go into phase 2. So somewhere around May 17, 18, things really start to heat up. And literally. And we end up with this blue section. So we have a whole bunch of fissures active about the same time. Volume is increasing. The lava flows make it to the ocean just already by the 19th of May. And so we've got these big flows. We've got a bunch of these lava fountains active. Lava's becoming faster moving. It's becoming more fluid. So it's dramatic increase in volume. When we look at the chemistry now, here's the blue, we're seeing it's basically approaching Pu'u'o values, although it sort of veers off a little bit there. And our temperature-wise, we're coming up to Pu'u'o values. So at this point, we again kind of let people know, we've basically reached Pu'u'o temperatures, and what does this mean? It means that the magma that was traveling through the pipeline has basically reached the surface. And oh no, what is that? That did not translate from Mac very well. Apologies for that. So what happens during that same time is that the geophysical techniques that they're using to monitor the volcano, so the deformation of the ground, for example, the ground outside Leilani, let me go back to the map maybe, here, was, there's stations on kind of this side of the fissures, and one on this side, and this one was basically moving to the north. So you can picture this blade of magma forcing its way down and pushing everything aside. So what we see is that thing is moving in, is this station is moving to the north. And so during this same phase that our chemistry is shifting here, basically right in here is where that movement stops. So it's opening, and the earthquakes go, and then everything sort of stops right about the same time that this stuff, we see this temperature change. And this is really cool, right? For us as geochemists, we don't usually ever get to see our data going along with the geophysics data at the same time. It's really pretty exciting to see that happening. And what that's telling us is basically the intruding dike is there. It's opened up, and you've got the stuff that was coming down is pouring out now. And so we have that correlation going on, which was, again, very exciting for us. So, maybe geochemistry can be useful once in a while. So then we get so that kind of goes on for a week, and about the 28th of May, things have basically shift back to fissure 8, becomes the main vent, and that big flow comes out, and that's when things just really, you get the huge flow, right, that goes to the north and goes around Kapoho Cone and out, takes out the whole coastline for the next 2 months. So here's the big channel, of course, big fountains coming out of fissure 8. So our lava now is kind of in this phase 3. It's in this hot, fluid lava, basically. So look at our trend up here now. This is trying to tell us something. So we see that it's going towards Pu'u'o, and then it veers off to this higher magnesium. Zirconium basically flattens out, right? We're done with the rocket chips. But for magnesium, there's something going on here. We're getting too much. Temperature-wise, it all levels out, pretty much stays the same magma temperature the rest of the eruption. Notice that it's a little bit lower than Pu'u'o. And the reason for that is that magma had to travel an extra 10, 15 miles down the pipeline to get to the surface. And in that time, it cools off a little bit. So we expect it to be a little bit lower. That makes sense. But the magnesium is trying to tell us something else. There's something in there that's hot. But we'll come back to that. Oh, the other thing that happened in here is these little purple dots. These are, so while fissure 8 was going, right, that everything is kind of pouring out, you've got this very hot, very fluid lava, there's a couple of these other fissures get reactivated. So they suddenly will kind of do little eruptions that would spit out a little bit of lava, mostly very small scale stuff. But when we could finally get to them, they were actually pretty hard. They were on the other side of that lava river, so we couldn't get to them until afterwards. But when we got some pieces and took them back to the lab, we saw, oh, look at that. These don't look anything like fissure 8. These look more like what we were seeing over here. Even one of them, fissure 22, even looked kind of like the andesite, or at least the kind of hot end of the andesite. So that brought up a whole other issue: is what is going on with that? Can these fissures actually mix? So, okay, so this is now two of our different incompatibles, right? Our normally rejected elements. Potassium is usually not taken into any minerals in a basalt. Titanium, though, is one that will, for a while, not be taken in, but at some point it'll start to. So what happens is if you have a really hot basalt here, and you let it crystallize, it would normally follow a pattern like this. Let's see the little dashed lines there. It's going to do something like that. It's going to get higher and higher in these guys, because the minerals are taking everything else out. They're getting concentrated. Then you get to a certain point where a mineral that really likes titanium comes in. It's going to start eating up your titanium, but it doesn't pay any attention to potassium, so that still keeps going up, but now your titanium drops. And I like this diagram because it helps us to distinguish these magma bodies from each other. So we've got kind of these colors are what we call our end members. So we've got here this end member of the andesite, very high in potassium, and zirconium, but not so much in titanium because it's in this in-between. It's already gone past that phase. Whereas our high titanium here, the Leilani stuff, the early stuff, is kind of in between. And these make separate bodies, but they sit on this trend that makes sense. If you take a magma, you let it crystallize and take out the crystals, that's the path it's going to follow. But our little purple things sit over here. So they're not on that path at all. They're telling us a story about mixing of those magmas. So not only do we have the stored magmas, but somehow in the system, they're getting mixed up with each other. And you're getting these mixed chemistries. So, so this diagram was our kind of one of our attempts to try to visualize this. So this is like the phase 1 stages where they're all erupting separately, and then they begin to mix. And while fissure 8's going down here, a little bit of this andesite seems to be mixing in with some of this other stuff and giving us these in-between eruptions. This little cone down here is fissure 22. This is beautiful little cone is doing some kind of little explosive things while fissure 8 was going, and erupted this material that was really very similar to the andesite. So clearly there was some connection at depth. And that was really cool to see, and to see, as soon as we could get those samples. Now, what are those magma bodies, right? We've got these 3 end members. This, of course, is whatever's coming from the summit and Pu'o'o. And these 2 guys, though, have to be these stored magma bodies. Now, where do they come from? There's a lot of possibilities. This is a map of the lower East Rift Zone. In light purple are the historic eruptions down there. The last one was in 1960, down at Kapoho and the lighthouse. 1955 had some eruptions off of some different parts. Before that, it was a long break to 1840 over on the north side. And then 1790 was right in that same area here, these eruptions here. So there's a couple possibilities for parental magmas, right? Things that might have gotten stuck down there and sat there crystallizing and changing and turning into possibly one or both of these magma bodies. Now this question is still wide open, and in fact there's at least 2 PhDs working on this now for their PhD projects on different aspects of this. So stay tuned, maybe we'll hear more about this. We basically just modeled a late 1955 as a possible parent. It works just fine for either one. So one of the big questions left on this then is, how long can magma sit down there and still be eruptible, right? Still be fluid enough to get back to the surface? How long does it take that fractionation to happen? There's some kind of 2 extreme models that people have published different things. We used to go with the old model of saying, well, it's about at 1 degree per year, in which case, right, none of the 1790 would be eruptible at all. Whereas other people have looked at the crystals and said, you know, this crystal's 500 years old. So clearly this magma's been sitting around a long time. So somewhere in between there is probably where reality actually sits. So we shall stay tuned to hear more about that, hopefully. Okay, so getting back to our secret olivine story, those olivine crystals floating in there were trying to tell us something. So Lopaka mentioned how we pick those grains out, we polish them up and send them in a microprobe so you can zap them and you not only get their chemistry, you get the chemistry of different parts. You get the cores and the rims. And this is a plot of, again, the days since the eruption, so starting at the beginning, going to the end. And this is going to be your amount, how much magnesium is in your olivine. Because as Lopaka mentioned, that magnesium goes up with the temperature. So high magnesium magma, you get high is hot, and you get hot, high magnesium olivine. So now these right here in gray, those are the Hawaiian lava lake samples. So remember we had the lava lake going for 10 years. Every once in a while we'd get Pele's hair and stuff kind of waft to the surface, and we'd find little tiny crystals in them, and Mickey and Brenna and guys would pick them out and put them in epoxy and polish them, and then we'd analyze them. And they all kind of came out right in the same area here, right about 80. Pu'uo'o had a little bit more variety. That's these little black triangles. But mostly this is right before the current eruption. Fischer's a little bit cooler than Haleakala. Makes sense. You know, it's a ways down the rift zone. But they're all pretty closely matched in chemistry. Okay, so the eruption begins down here with the yellow guys. Very cool. Makes sense, right? They've been sitting there crystallizing. It's a cooler magma, so you have lower magnesium olivine. Great, that makes sense. Next batch, okay, they're getting hotter. Already starting to overlap with Pu'uo'o. That's interesting. And then we start getting into here, and all of a sudden, about 20 days into the eruption, we find olivine with almost 90% magnesium. Now that, you need a magma of about 1,300 degrees to get that. So that's telling us something really unusual too, that this is not Pu'uo'o magma. There's probably some mixed in, you'll still see a bunch of stuff at that level. But that this eruption is so disruptive to the system that it's scooping up some hot, deep olivines and mixing them in and carrying them down the pipeline. And they're growing rims, so the open symbols here are the rims. So when we actually zap the edge of the crystal versus the center. And those tend to be around this line. This line is sort of the theoretical line for what they should be if the crystals were growing in the glass, in the melt that they're in. So that's sort of what equilibrium line. So if the crystal was formed in that liquid, that's what it would look like. So it's telling us that most of these crystals, at least their cores, formed somewhere else. And then as they travel down, maybe they grow a little rim as they're going, and that's going to match more with your glass. But we were picking up this really deep hot stuff. So we have a whole nother thing going on that you couldn't even really tell, except that magnesium went kind of wacky. So if we put it together in a diagram, our sort of theoretical slice through the volcano, we've got our so this is a summit up here, and there's the what we sort of pictured as the sort of arrangement of magma chambers under the summit. There's kind of was at least a shallow body right under Haleakala, and then the deep south caldera body. There was a lava lake up there, and it was feeding the Pu'uo'o eruption, so that kind of system right there was going on happily for at least the last 10 years. Of course, Pu'uo'o for 35. And then something broke, basically out in here, and stuff started moving. So the numbers here are our different end members, our different magma bodies. So in yellow, that's our Leilani. So the dike comes down, pushes the stuff out, starts mixing with it, hits this one, pushes it out, gets some mixing in there, and it's mixing with the 3, which is our kind of our summit Pu'uo'o stuff. But somewhere along the way, it's scooping up some of 4 as well. And one of our ideas is that this magma up in here, the shallow magma chamber, that was open to the air, that magma was circulating in a lava lake, and it cools, it degasses, it gets dense. And so when you start to drain that, it's denser than the lava around it. It's going to sink and potentially stir up deeper levels of your deeper magma body. And that's potentially one of the ways we may be getting those hot olivines mixed into the system. There's other possibilities, but that's one that seems quite likely. So geochemistry, telling us a little bit about what's going on. We need the geophysics, but the geochemistry can help too in trying to decipher what's going on. So basically, it was exciting for us to actually have this work, after all these years that these guys worked on it, where nothing changed, right? Over 5 years, we kept getting the same numbers over and over again, and it was hard to prove that this was worth it. To finally have something happen was very exciting, I think, for all of us to see, and to actually be able to contribute a little bit to the hazards, to the monitoring, to the interpretation of the eruption was exciting for all of us, and hopefully I haven't put you all to sleep yet. So thank you all very much.